Okay, there are a couple of questions, obviously, on the notion of absolute, the tests, for convergence. Um, yeah, it's very important that we do a wide range of questions, and I'm sure that I can always bring a bit more questions. So I'll have to scavenge for the questions a little bit, okay, because there are all sorts of all over the place in the textbook and so on. And the prescribed textbook surely has more of them, and I'll have to try to gather those. Okay, but by and large, this module is direct in the way the exam is always structured. So the first question is about the what we call the divergent or convergent series. So given a series like this, we always use the vanishing condition. So now, what we do in view of the vanishing condition, we simply consider this series here and actually then be in a position to solve this using the vanishing condition principle. What does the vanishing condition principle state? So what we do then, we consider the limit. So we consider. So the first question, by and large, always require the vanishing condition in this module. So it's just some sort of the structure. So we consider, therefore, the absolute value. I consider, you can call it AN. To be -1, so you just replace every R by what? By N. Right, in which case, therefore, you have N squared plus N, right? Minus the square root of N squared minus 1. Okay, it's exactly this, but we've just put replaced every R by N. So, and that means we always take the modulus of the AN term. And if you take the modulus, it actually removes the alternating powers of the -1 to the power something. So you have the removal of that minus the square root of N squared minus 1. Okay, you have this. Okay, when you get these now, what do we do? Okay, we have this. But yeah, I decided to maintain this. The fact that if there's a minus between the expressions, it's best you just maintain the absolute value or the modulus, because the expression might become negative because of the minus in the event that this expression is bigger than that for some value or some values of n. It might always be less, in which case it can be argued that this is always a bigger number minus a smaller number and so on, in which case, therefore, it can make sense to drop the modulus sign altogether. All right, so we have this. So this implies that. Hence, we have this. After that, we therefore multiply these by the square root of n squared minus n minus the square root of n squared minus 1. We divide, okay, we multiply by the opposite sign of this, for example, remember? So yeah, the problems will just require the vanishing condition. So in the case of the vanishing condition, we just only take the summand, right? And after having taken the summand, we just take the limit of it. But obviously at this point, we can see that what we have here is rather very, very, well, we can't take the limit of this at this point, right? Since we can't take the limit of this, what do? We then are in a position to take the limit of this, okay, by rationalizing first, right? Just a sec. right? See, these are the display options. Display options. Right. I press something now, and the screen just went. Is that? Can I just restore it? Okay. Right. So we have this. So now we continue. So we therefore continue to rationalize. So we just change the sign of the middle. Right. So in which case you have n squared minus n plus the square root of n squared minus 1. So what have we done here? We are rationalizing this here. Why? Because we want to take the limit of this. But if we take the limit of this in view of the vanishing condition, because by the vanishing condition, we just need to take the limit of this expression, in particular the modulus of that, so that this one is out. But we can't, if we take the limit of this, it becomes, because we take the limit as n approaches infinity. So we have too many problems because it becomes infinity minus infinity, etc. So in infinity minus infinity is indeterminate, is actually an indeterminate form, which therefore means that we need to multiply this with that. So it becomes n squared minus n. This with that, right, the square root is going to go away, so giving us minus n squared plus 1 divided by the square root of n squared minus n plus the square root of n squared minus 1. So what do we have? Right, so we have what is actually at the bottom. Right, let's look at the numerator very carefully. It becomes a difference of 2 squares, in which case, therefore, just multiply the first expression. I need to bring my 2 here. Right, I need to bring my 2. Right, so where is my 2 now? It's here. Just a sec. All right, so we have that. So after that, what do we then have? Right, so we then have exactly what we got. But I was then saying, with that, then we have this. If we have this, we just need to make sure that our algebra is not having any algebraic errors in the way we manipulate the terms. In the numerator, for example, we shall have, therefore, 1 minus n to divide everything by the square root of n squared minus n plus the square root of n squared minus 1, like this. Right.
Hello?
Yes, please.
For this question, why don't you use the ratio test?
Okay, that's a good question. Right. Why would we not use the ratio test? Yeah, you see, that's the thing, because some of the tests one can always try them and experience a problem with the test. And then, for instance, my suspicion is that the ratio test here will actually yield the limit 1, very likely. So I mean, one can always try that and conclude that doesn't work. But just that in this module, the first question always works with the vanishing condition. So yeah, but can the ratio test not be used? Well, it will only be if it fails to work. When does it fail to work? It fails to work if you take the limit and the limit becomes 1. Because if the limit is 1, then it is inconclusive. You can't say if it's convergent, if the series is convergent or divergent anyway. So we'll have to try and see how that is going to obviously work out. Okay. So otherwise, this is exactly what we get. You see, I made a small error here because this is r squared plus r. So this must be plus, and this must be plus. This must be plus. This must be plus. Okay, it was even worrying me because I was wondering how the examiner would put a minus there, because it would bring a problem when you have infinity minus infinity under the square root sign. All right, I just realized that it is a plus. So just to make sure that we maintain it that, so this one is also plus here. It's n squared plus n, then it is this minus that. So which means therefore we shall have the n squared cancelling, and this is going to be 1 plus n. Beautiful, beautiful result now. Okay, so okay, we're going to try the ratio test. Thank you. Right, so hence, or thus, we get the limit as n approaches infinity of an, with the limit as n approaches infinity. So you have 1 plus n, which is divided by, you have n squared plus n plus the square root of n squared minus 1 like this. N approaches infinity. So you factor out n from the numerator, because if we just use the word substitute, we in mathematics we say if we take the limit of the function as n approaches infinity, okay, if you take the limit, but now if one uses the word substitute, replacing every n by infinity, what we get here is infinity over infinity, and this whole thing becomes indeterminate and it is undefined. So we're going to factor out algebraically, we're going to manipulate this and have 1 over n plus 1. Okay, the vanishing condition does not always work for all series anyway. So we have n that is going to be factorized from the denominator. Okay, but if we factor out n from the denominator from under the square root, for us to have n here, we must factor out n squared, whose square root, and the square root of n squared is n. So if factor out n squared from here, we have 1 plus 1 over n plus, and then here, n squared is the same thing, 1 minus 1 over n, like this, right? So this is the limit. N approaches infinity of 1 over n plus, the n cancels, 1 plus 1 over n, the square root of 1 minus 1 over n. As n approaches infinity, this one is 1 plus 0, and 1 plus 1 is 1/2, which is not 0. Okay, if it happens that this limit is not 0, hence we infer by the vanishing condition that the series, because we're dealing with a series, the series is what? Is the divergence. So that is exactly what we say. So just to note the use of this vanishing condition. Obviously, a good question from you. Can we use the ratio test? Well, the truth is, in mathematics in general, we try any test. Multiple tests can work. Okay, let me see what the chart is saying there.
I sent you 4 questions. These questions, the answers, they use
Yeah.
the alternating series test, ratio test, integral test, and p-test.
Yeah, okay. Let me see. Okay, so this is exactly, we can try to sort of magnify this. Okay. Okay, if we look at these questions, They're from an exam, right? Okay, yeah. So by looking at these questions, what test would work? Okay, in this module, it has become so obvious to spot the test, but I know that we can always have a discussion, a textbook discussion about the textbook collection of problems, which is a mixture of different tests. But obviously, by looking at these straight away, one can see that these, what we're getting here, for example, is a is most certainly a mixture of things. Let me see. Let me just exit here. Just one sec. All right. It becomes therefore a mixture of things. So, right. So let me just expand this a little bit so that we can have an so look at these questions and try to make sense of this. All right. So right, in view of these questions, can we, for example, I mean, I'm trying to put myself in your shoes in terms of thinking about, can we use the ratio test for each of these questions? For example, can the ratio test work all the time? Well, the truth is it doesn't work all the time. And there are instances when it fails. And a good example would be to try and apply it here and see what it gives us, you know. So I will just take this one, put it here, and we try the ratio test here, for example, and see what the ratio test is going to give us. Okay, but you try, okay? So obviously under exam conditions, trying is, but in this module, normally you don't try, you know the questions. How do you see that you need to use the ratio test as well? Okay, let's see. So you can let an be the modulus, so just take the absolute value of this, and then you have n squared plus n minus this one, which is n squared minus 1. Thus, okay, once you get these, we're trying the ratio test. So we're going to, so the absolute value here. So you must take the absolute value called an, etc. But this an is absolute value of the right. So you must maintain that. Right, the ratio test therefore has implications about the limit as n approaches infinity of an plus 1 over an. This is the limit as n approaches infinity. What is an plus 1? N plus 1? N plus 1? N plus 1? All right, so we'll just put the n plus 1 there. Okay, so obviously, I mean, I'm just directly applying the ratio test to see if there are any problems with that. Obviously, it will require a bit more work, this question, because if we take we're applying the ratio test, it's okay, but we can just play around with this and we can try to evaluate this limit, right? So, for instance, if we divide in the place of n, we've put n plus 1 here everywhere, and here in the denominator, we have this one. And then we have n squared minus 1. Okay, so which is the an? I've put it just at the bottom. Then how do we evaluate this limit here? Because if you let n approach infinity, then it's going to be infinity squared plus infinity. So it's infinity minus infinity, indeterminate, infinity minus infinity. But again, it's this over that. So it's infinity minus infinity divided by infinity minus infinity. So which means we just have a fiasco to deal with because this here is said to be indeterminate. The numerator alone is indeterminate. Okay, you see the indeterminate nature of the, but also the whole thing now to say, what is this? If you divide an indeterminate form by an indeterminate form, what do we achieve? Okay, but it means we need to perform some algebraic manipulations of this. We need to rationalize this, rationalize the numerator, or we can alternatively just rationalize this from the beginning, right? And then plug it in here, rationalize already. If one rationalizes this, what does it become this? We saw here, don't want to, we saw that it becomes, after rationalizing, 1 plus n. It became n plus 1. Divided by n squared plus n plus the square root of n squared plus 1. Okay, so it means that anything, this difference here, which is leading to indeterminate forms, can be handled better. We have the limit as n approaches infinity. What is this? It can be written like that. So the top alone, we can write it like this. We can write it as this one here. Wherever there is n, we put n plus 1 here. So we can put n plus 1 wherever there is n. So this one is going to be n plus 2. Wherever there is n, we put n plus 1. So it's going to be n plus 2. Right. So it's going to be n plus 2. You divide by the square root of n plus 1 squared plus n plus 1, like this. So plus 1 here, like this. So now, this is just only the top. The bottom, this one is like this, but it is equal to this. But because it's in the denominator, then we invert it. Or it's going to be this. Okay, we're just looking at how we can apply the ratio test here and see what problems normally it gives. Hey, what is this? So this is actually the limit. So we have this. And then you have, oh no, see now, I'm looking at another thing. Is this, so you are dividing by this. Okay, we're gonna just evaluate it on the other side. Plus n plus 1. Okay, okay, you have this, n squared plus n. You have this here. Okay, we divide by this. We're just trying to apply the ratio test, okay? So we have this. We have n plus 1. Where are we now? Okay. Right, this is n. So we have this. Whereas n approaches infinity, okay, we can just write one more step and then we're done. Right, so we're gonna factor out n from the numerator, which leaves us with this. We factor out n from the denominator, and it leaves us with 1 plus that. Why? Because if we just take the limit straight away, infinity plus 2 is infinity over infinity, and indeterminate. We also factor out n from here. So we have this. Okay, so we have this. Okay. Want to factor out n squared out of this. How do we factor out n squared out of this? Okay. If you factor out n squared out of this, you must factor out n. And then it's going to become n squared. And then it's going to go out as n. If you factor out n out of this, you have this. Right? So here would have n squared. But if you factor out n squared out of n, we obtain, factor out n squared out of n, we have this. But when you multiply this by n squared, it goes back to that. Also, if you factor out n squared, if you factor out n squared out of 1, you get 1 over n squared. Because when you multiply, it becomes 1. Okay? So we have this. What is this? Okay, we're just trying to apply the ratio test, please, to see what it's going to give us. The vanishing condition surely works. And then here, if you factor out, here you must factor out n squared because we have a square root. So, but if you factor out, you must factor out n out of these because there is a perfect square. This n plus 1 is a perfect square. So you're going to have 1 plus this. Okay, this one. Plus and then now you have factor out here, you factor out n squared, which is 1 over n squared. Yes, like this. So n squared cancels out. So this one cancels out, giving the limit as n approaches infinity. Okay, anyhow. So let's just take the limit straight away and analyze this expression by expression without wasting much time already. Just to carrying on with all these radicals. Okay, what we achieve out of this? So what we're able to achieve here is that this one here is going to be 1 plus 0 over 1. If you take the limit as n approaches infinity, these things will approach 0. If you take the limit, then this one is going to be 0, 0, and then it's going to be 1 plus 1, which is 2 out of. This one is going to be 1, 0, 0, 1, 0. See, so now the whole thing is 2 out of 2, which is 1. So the ratio tests, when you find, we're using the ratio test, when you find that this, so it is inconclusive. So we can't determine by the ratio test if it is convergent or divergent, and hence my suspicion. So what I'm saying here is, even if here these questions, like this one, can we use the ratio test? Normally, because this one is involving some polynomials under the square root. A problem like this, something you can use also is the comparison test. Or the P-series test. Okay, I feel like you need more questions, but let's look at these ones. For example, like this particular question. What is happening with this? And what test can we use? Well, my immediate suspicion, because it is in this exam for this module, the vanishing condition is the one to try first. And if this limit is not 0, then we have a divergent series. So let me just do that. Right, so just want to explore these questions you gave. Let me just add a bit more slides here so that we can practice that one. Right, let me just add more slides so that we can just look at the questions you brought. Right, and explore the tests. But yeah, in this module, we use a limited number of tests, but it will be very interesting to look at billions of problems from a pool. Yeah, because some of the problems can be normally very challenging in general, because you can look at a question and be like, it can defy some tests. And now you can, like, this test doesn't work. Like the ratio test failed there. So if it fails, what do we do? Right, if it fails, like the first one, my immediate suspicion there is that the vanishing condition is going to work. Let's try the vanishing condition. All right. Okay. But another test that we can use the comparison test. What does the comparison test say? The comparison test says that we can extract some things from it. Right, we can extract some higher powers and higher degrees. Okay, first, normally, what predictions can we give here? You look at the things that are easy to integrate, like this one. Because there is a square root here and a square root there, it can be integrated such that if you integrate, this one cancels this. The immediate one to use is we want to integrate, so we can use the integral test. Okay? Can you use the ratio test? My immediate suspicion is that this one, because it is having r square root over square root, is just going to be 1. And the ratio test fails, it is inconclusive. We can't make any conclusion in terms of the convergence divergence. Let's look at 3.1.1 first. Right, so we have the limit as r approaches infinity. As r approaches infinity. Okay, I'm copying the wrong thing. I want to copy the series first so that we can use we'll come to the limits, obviously, in view of the vanishing condition. We take the limit, but first, I want to copy the actual series. So the series is going to be this one. Right, so you have this series. 1 to infinity minus 1 minus 1 to the to the r plus 1. So you have the square root. Okay, so Minus 2r. Okay, this one, because it's the first sort of question and it involves a square roots like this. In this module, these kinds of questions from the bank of questions, they just put them together. So these questions are ordinarily not new when they come in the exam. Right, so you need to let an. So you have r here. Anyway, can we make it n? Like that. So we have this. Okay? We need to take the limit of this, but we can't take the limit because it's having a minus. So this is going to be infinity minus infinity. So hence. Okay, we need to rationalize this because there's some square roots. Okay. Like the other one. So if you rationalize the vanishing condition, says that if the limit is not zero, then we have divergence. We must just show that the limit of this does not approach zero. So, right, so we're going to do that. Right, so because it's minus between this, so you put a plus. Okay, like this. Okay, like this. This times that. Um, so we have this. Right, so which means therefore you have n divided by what? The square root of 4n squared plus n plus twice n. Right. Hence we have the limit of this n squared to n. And therefore, this is exactly 4n squared plus 2n. You factor out this one. It's n here, n, so you can even remove the absolute value here or the modulus because the everything is plus and n approaches infinity. So the n's themselves, the values of n are positive. So which is 4. This one, you factor out n, and you cancel the n's. Okay, just jump to a trivial step there, but there's going to be n that we factor. You factor out n from this. This is going to be 4 plus that, and this is that. So as n approaches infinity, this whole thing, this is going to approach 0, which is square root of 4 is 2, plus 2 is 1/4, and 1/4 is not 0, and we have divergence by the vanishing condition. Right, so what we have is divergence by the vanishing condition. So, right, so now the question is, can we use the ratio test for this one? Surely the limit will just be 1 of this, like we saw before. So the ratio test is inconclusive in terms of the, so it's not going to allow us to conclude whether it's divergent, convergent if the limit is 1. Because if ever the, so this one is divergent. Right, so it is divergent. Right, so those are the kinds of things. Right, so this one is divergent. Okay, so we have 3.1.2. This one, is it divergent or convergent? What test can you use? Like as I said, this is proposing, suggesting that if we integrate, then we let u, and if we integrate, the square root is going to somehow cancel with this, etc. So that's sort of the idea. So the integral test becomes the most appropriate. What other tests? Other tests can we use as well? Okay. You see, there's also the notion of conditional convergence. When conditional convergence, because if ever we use the integral test, and this one becomes divergent, which is possible because I've not done it before, quite. All right, it can be divergent. If ever it's divergent, then we use the alternating series test. Then it becomes conditionally convergent because it was divergent, but it is convergent because of what? The alternating series test. Because now, if we use here the integral test, which we're going to use now, if ever we find that it is divergent, how is it divergent? That one, okay, it's divergence because first and foremost, it must be a decreasing function for us to use the integral test. Decreasing function, so we can test this. Okay, so yeah, it's 5 marks. And then you might have the conditional convergence, or otherwise it might be fully convergent. In other words, you might have absolute convergence, right? So let's see this. Right, so I want to try this one. Series, see, series 1 to infinity. Right, so we have this series. Which is -1. The power r. Which is minus the square root of r. So we have this. So if you look at this one, what test can you use? Okay, we're proposing the integral test because the function is clearly decreasing because it's exponential. But also, if you, this one has a negative exponent, if you bring it down, it's going to be make this the denominator very large. If the denominator is very large, so it's going to be decreasing. All right. So the integral test becomes the immediate one to use. So we let an. Okay. So obviously, if we let the integral test, normally we use straight fx, the f function. So we call it, we change r to x. So let f of x. All right. So we let f of x. You remove this one, and it becomes e to the minus the square root of x. Square root of x. But x now from 1 to infinity. Yeah, can write it like that, but you can write it as an interval. So x is an element of the interval from 1 to infinity. Right, so x itself is an element of the interval from 1 to infinity. Like this. Okay, so now we integrate the integral of this. We do the integral of this 1 to infinity. Okay, this one is decreasing. I'm gonna state that one. How do we know? We can find the derivative and show that the derivative is negative all the time, but its decreasing properties are just very obvious if you look at, but you can't say obvious in the exam, please. Right, so you have e to this. Because this is the exponential function, it increases, but if it's in a denominator, it makes a function to be decreasing. But for us to sort of conclude, we need to use calculus to do this. So if we want, we can make this a product, so that we can use the product rule. So we have x this. So you have this. So we have this. And then you have this. So we have this. So okay, I just squashed it here, but this one is negative, and this one is negative, so this whole thing is negative. So we're decreasing. Decreasing, therefore, we take the integral of this, right? But obviously we integrate it from 1 to infinity, like the summation of this. Right. We'll remember a common practice, and the tendency is to take this one. Okay, look, the tendency is to take this and use something I want to say here. Right, so the tendency is to take the test like we normally call this the JN. Use the JN notation. So if you use the JN notation, it means what? Right, the JN notation means that you're gonna call this JN. Right, anyway, that's fine like that, but yeah, you can call it because it's an proper integral either way. So you can call it JN. It's popular. So instead of just calling it solid, it can make the integration easier. They call it Jn like that, and then it's going to take the limit at the end so that it can go to infinity. Right? So we want it to behave well. Now, what is this? Okay, just we need to just integrate this. So the integration of this uses first-year methods. What are the first-year methods? Okay, wanted to remove this. You let something be something, etc., and cancel something else, like in first year. So we could let u be the top. You can take u to be the square root, negative the square root. What is du? Is 1 over 2 the square root of x dx, like this. Okay? So, which therefore means now we have this integral here. Okay, what is dx? Okay, this one, what is square root of x? Is minus u here from here. You put minus u, we're changing the variable. What is dx? Dx is minus 2 the square root of x, which is minus 2u. So we have x and u. So we have this. From 1 to that, u, if x is 1 to that, because this is in terms of x, u is going to be minus 1 minus the square root of n. So 1 corresponds with minus 1 minus the square root of n, something like this. This u now is going to cancel this. Negative and negative are going to cancel out, giving us a positive u, which is that. Okay. And then you have u e to the u du. Okay, next page. So we've got that Jn is 2 the integral of minus 1 to the minus square root of n, and then you have what? U e to the u. Okay, now you need to just integrate these. What is the integral of these? Okay, so because now we're integrating a product of functions, we use integration by parts. All right, integration by parts. What is integration by parts? The formula for integration by parts is that it says the integral of u dv is uv minus the integral of what? The integral of v du. So we use this. All right. In view of the question, then we're going to have to let things here. Choose u and choose v. What is u? What? Choose u and choose dv, actually. Right. So u is the thing that can be easily differentiated in such that it dissolves. So you can let u be okay, because you already have u here. Okay, so right, you can make the change the variable because this one is also u, this one is also u, so it's not nice. It can give us some problems and you can get confused. So you can change this one and use some different variables. Use t. T is u. Then say u is t here, and v is the okay. Ah, okay. This one is du, so it must be dt. Must be dt. Okay, these are just dummy variables. These symbols, so should not quite be concerned about this. I just change every u to t, so that you can be able to use this without this u confusing, leading to a confusion with the u in the integration by parts formula. Right, so you have dv, therefore equals e to the t dt. What is du? Is dt. Okay. Where is dv? Where is u? V. Mm, so we have this. Okay. Now this is Jn. So we have this. Right, so substitute everything here, these things, and okay. Want to see what's going to happen if this is going to be finite or infinite, divergent or convergent. So we substitute wherever there is t, we put this top one, minus we put the bottom limit of integration, which is the lower limit of integration. Okay. All right, so we must take the limit now. Okay, we're still obviously determining absolute convergence. In other words, what is absolute convergence? It's a convergence of the series that involves the absolute value. Is this approaches infinity, what do we achieve? We take the limit of the Jn. So we take the limit of these things here. I've just pulled out the 2 because it's what? The constant. So we have minus the square root of n. Here you can divide by the e. Make sure that it becomes plus here. Right, and this one is 1 over e. Okay, as n approaches infinity, you realize that this is infinity over that. So, but in general, if this one approaches infinity, this one here, you can integrate. You can rather differentiate the top end of using L'Hopital rule here because it's infinity over infinity, so you can use L'Hopital rule. And if you use L'Hopital rule, then I can just use that to avoid making a lot of assumptions about the behavior of these functions. Well, it is expected that the denominator is going to be very large because it's going to increase exponentially, but the denominator is going to approach infinity at a slower pace. In mathematics, we therefore say if the denominator is very large, but they both approach infinity, the result becomes 0. But however, you can just be gentle with this and use a bit more practical and very evident methods. L'Hopital rule can be used. The derivative of this one is 1 over 2 square root. And the derivative of this one is 1 over 2 square root. So what is happening here? Can you simplify this? So the top would be 1 over 2 square root. The bottom is going to be 1 over 2 square root. E to the square root, like this. So we get this. Right. So now this one cancels this. By L'Hopital rule, this thing becomes this. And then this one, you can write it like that. There's no problem with this. And then you have 2 over e. This thing, what does it give us this? Right, so this is 2 into. So this one is going to be 1 over infinity, 0, 0. And then you have 2 over e, which is 4 over e. And 4 over e is a finite number. And therefore it means that this one is convergent. Because it's convergent, then it's absolutely convergent. Absolutely convergent. Absolutely what? Convergent. Okay, because it's absolutely convergent, we have concluded, so there's no need for us to test for other things like your um the alternating series test. If only it was divergent, yes, we could test. Uh, we could proceed to the alternating series test, but at this point, no, there's no need to go through the alternating series test because already it is absolutely convergent. The series of the absolute values is convergent, and because it is convergent, right, we are good. Right, we are so good. Okay, right. Next, we look at this one. What do we use here? This one, because it's like this, it has a square root, which we could use also for this. Use this one, uses the P series. Uses the P series. How do we use the P series? We must just remove the square root to use the P series. Right, so, and then we use just the P series for 3.3. Let's just proceed to use the P series for 3.3. What test can we use for this one? Because we can see that if you multiply r with r here, r over 2 times 3r, it becomes 3 over 2r squared. The r squared suggests the P series, but the only problem is the square root. So now we're going to use the square root. We're going to just remove the square root in a clever way. There's a way we remove the square root. How to remove the square root is as follows. Okay, let's look at this one. We're looking at the one that is 3.3. It is the infinite series. So you have r over 2. Okay, this one. How do we go about this one? So this one here, we're going to use the comparison test. We call it the limit comparison test. Plus P series. Plus P series test. Okay, so normally this one, we always do that. You see the problem in this module, the problems are, I think that in my next discussion, if we agree to have another discussion, I'm going to bring the textbook problems so that we can just play around with more detail because the exams are normally very limited in the way the questions are asked. So we play around with the same tests the whole time. So yeah, that is what is happening there. But let me see. Let me see, let me see, let me see. Right, 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 right. Right, we continue. I was saying then we need to just limit comparison test. Okay, so we have n over 2 into 3n plus 4. All right, so what would this one be, for example? Now, because we have the square root like this, put that and choose Bn. Okay, and hence the P series is going to come into the picture. So we choose Bn. What is Bn now? Bn, we remove some of the things like we're going to remove the 4, the constant, because we just need the higher power. So we can remove even the 2, okay, because it's not going to affect the thing that affects in the P series is the power of the n. So we can choose here this n into n like this, and remove the 4, remove the 3, remove the 2. Okay, and then now this one is 1 over the square root of n squared, which is 1 over n. Okay, this one is called because it is to the power 1. So it is a P series. Because P series means you have 1 over n to the power P. P series P is 1. And then it is divergent. We're not saying this one is divergent. We are effectively saying the BNs form a divergent series on their own. But in view of the limit comparison test, so we're not done yet. The fact that this one is divergent, so we must now continue to show that the limit of the quotient, then AN over BN. What is AN? BN. Okay, AN is this, so you can just copy this. All right, and then now you divide by the BN, which is this. If you divide by the BN is the same as multiplying by the reciprocal, from which we have this one. The top is that, the bottom is that. Right. Okay, we need to just, okay, let's just multiply under the square root here. So that we can be able to evaluate this limit, we need to cancel out this n with something. So we need to just be able to factor out carefully under the square from under the square root. So we can multiply this one, it's going to be 3n squared plus 2n. So we have 3n squared over 2. 3n squared over 2 plus 2n. So, okay, we factor out n from n squared under the square root. So this is 1 divided by n squared here. Okay, you factor out n squared and this becomes 2 over n. You get this? Okay, if you, the n is cancelled now. I factored out n squared, but the n squared, if it goes through the square root, the square root of n squared becomes n cancels with this. So this one is going to be 3 over 2, but if you factor out n squared out of the 2n, it becomes exactly that one. Okay, Let me see. Um, okay, so we have this. So therefore, as n approaches infinity, you have this one is 0. So it therefore becomes this. Okay. So this thing can be the square root of 2 over the square root of 3, this. Right, and it is not 0. Right, since it's not 0, since this series here, this one here of the 1 over that, now we bring back the r, because it just became 1 over n, which is 1 over r. Since this one diverges, because it is a p series with p equals 1, p equals 1 is divergent. So there are two cases when the p series diverges. It's when p is 1 or is when p is smaller than 1. Then the p series diverges. What is the case whenever it converges? It's when p is 2 or more, when the p, n squared will always converge. Okay. So since this one diverges, it follows that this series here this original one diverges. It diverges. So okay. So this one diverges. So this one surely diverges. Okay. So we have that experience there that it diverges by the limit comparison test. So because it diverges, what do we do? It might be conditionally convergent. So we must now proceed to check conditional convergence. Okay. Because it's alternating. If it was not alternating and this was not there, then we're gonna say it's divergent and it's the end. But it's not the end because the alternating series test can change this. It can bring another condition here. So let me just include one more slide here. So I'm gonna just add 2 more slides so that we can just look at the alternating series test for this. Okay, let's just continue. Okay, we're looking at these now, and then we decided let us obviously use the what we used the limit comparison test. Limit comparison test. That's what we use. Limit comparison test. Okay. Now I haven't used the limit comparison test. Now using the alternating series test because we found divergence. Alternating series test. What is the alternating series test? Okay. Alternating series test, we actually do what? We use it as follows. Because this one is an alternating series, so we consider this series. Uh-huh. Right, so we consider this series. Right, so we consider this one here. R equals 1 minus 1 to the r e to this. No, not writing. This is the other one we just did. Right, this one, 1 over. This one here. Like this. You consider this one. And then now we're going to use the alternating series test. What does the alternating series test say? So in other words, we consider that the summation r equals 1 to infinity of AR, which is this one here. So we have this. Right, so we have this one. So we extract this. Alternating series test says that if you have this here, we can write this.
Hello?
Yes, please.
Why are you using the alternating series test?
We are using the alternating series test because we found that it is divergent, but it is alternating. Right. If it is divergent and it is essentially alternating, then there is a chance that it can be conditionally convergent. So we need to test if it's not conditional convergent or not. Okay, so that is what obviously we say there. That is what we say. Okay, there's something I want to say here also. Just 1 second here. I want to give one statement about the limit comparison test. I want to give one statement about the limit comparison test. Okay, I'm going to give one statement about the limit comparison test because it's a very, very important test. Right, it's a very important test that we use all the time. Right, the limit comparison test has those two conditions. There is more information about the limit comparison test that I need to give. Okay, let me first speak about the properties of the limit comparison test. Let me speak about the properties of the limit comparison test. Right, so the limit comparison test. Right, it says that if the limit Yes, n approaches infinity of the quotient of the an and bn. An over bn. If it happens that this one here is a number c, where c is finite, is a finite positive number, like this. Both the summation we have these converge, or both diverge. So now you have the limit comparison test. If this is that, where c is a finite positive number, both these converge or diverge. Okay, so that is what we say. So in particular, I would mention that in view of that, strictly speaking, you can actually make the, interesting that this can't erase. How possible is that? Okay, oh, I did not pick the eraser. Okay, just 1 sec. Okay, I'm using the eraser, but it's strange that I can't erase this. Okay, but my point is, in view of that statement, a strict condition would be this is finite. It's finite, it is smaller than infinity, and therefore the obvious is divergent anyway. And what conclusion can we draw out of this? Okay, so we have this. Okay, I was saying here, this is the limit comparison test. Normally it works when you have problems like these that can convert to p-series like we did. Right, we have exactly this here. Okay, my point then is after this, because we have seen that these diverges, right, we have seen that these diverges, then we proceed to use the alternating series tests. Refer to the study guide. This example is very much like the one in the study guide. Right, study guide pages 21 and 22. Okay, this example also is there in the study guide, where there is a situation where although there is a small error in the way the whole thing is being written there. But we have the alternating series test, which is used in the case where the p-series is implying divergence, and we have divergence, and therefore we use the alternating series test because it might be conditionally convergent. Okay. So now in view of even the study guide, pages 21 and 22, we just need to infer that this function is decreasing. So we take BR to be this whole thing without the alternation, one out of, like this. We argue that this one is decreasing this. Sometimes it's tricky to see, but decreasing would mean that you need to just compare BR and BR minus one, BR plus one, excuse me. If it's decreasing, then it means that if you compare, if it's decreasing, then it means that as you go take larger values of R, it is smaller. And this would be decreasing. So this can be simply by simply testing with numbers. Like if you get B1 here, or you can use calculus and find the derivative of this. Right, B1 is what? This one is actually 7 out of 2. What about B2? B2. Okay, you can do B2 here. So this is a 2, which is 6 plus 4, 10. Okay, we're adding everything. Right, 2 here is going to become what? It's going to become 6 plus 4, 10. And then this is 2 over 2. Okay, beautiful. 10. So we have that. So the B2 is just 1 over the square root of 10. This is B1. This is B1, and this one is what? Is B2, which is, we found it to be 10. Which one is smaller than the other? Because this one, 7 divided by 2 is what? Is 3.5. So if you compare B2 and B1, which one is bigger? Right. So obviously you can see that this B2 is going to be smaller because the denominator is very big, bigger than this. So it means it's decreasing. Right. So does it decrease for all n, or is just this B2? Well, we expect it to decrease for n. This also, from 1 to that, you can think about this function under the square root. It's a quadratic function. How does it behave? Does it have a turning point, perhaps, that it is increasing and then it starts to decrease after turning point? So that kind of thing. So perhaps the safest way of it is to use calculus to find the derivative of this. Right, but now it is expected that thus this is decreasing, but you don't want to make a mistake there and make that kind of a conclusion. Right, so we suspect, I can use that word, we suspect it's decreasing. Right, because we need a general proof. Otherwise, then we can just, because the function, this is a quadratic function, this parabola, it has a positive coefficient there, so it's going to have a minimum vertex like this. So the minute it is increasing, we expect it to increase all the time, okay? So we suspect that BR is what? Is decreasing. Because the function obviously is increasing there. And then we use calculus. Next page. That's lacks how to prove in general. We must use calculus. Okay, because the examiner might dispute a conclusion that is not sufficiently backed up. So we let f of x, which is 1 over 2 is 1 divided by. So we have this, and then we find the derivative of this. Then you have this. Okay, clearly this one is negative for all x which are from 1 to infinity. The summation is from 1 to infinity. Okay, so we have a decreasing function. Okay, because this one is a decreasing function, what do we do? We what next do we need? Because now we know that it's decreasing. We need to find the limit of this. The limit of the Pn must be 0. Right? So we just are left with that one. So we say also the limit as n approaches infinity of this one. We get the limit of an now, not just Pn. Right? So it's 0. Okay, this limit must be 0. If this limit is 0, we celebrate and we say we have got it, and we use expressions like Eureka after some of the scientists that existed and celebrated profound results and discoveries. So therefore, this one here, which is the original, so this one converges by the alternating series test. By the alternating series test, and hence we conclude that this series here is conditionally convergent. So it was divergent before, but now we found that it is conditionally convergent because it is the alternating series test that is bringing about convergence. So we conclude that it is what? It is conditionally convergent. Okay, so that's one thing that we just have observed. Okay, as I said, in view of the study guide, so we continue. Okay, let's look at the question 3.1.4, which is the last one in the set of questions you brought. Right. This one here would be what test first and foremost would work. So we look at it and think very carefully. Right. Look at it and think very carefully. The ratio test generally, when does the ratio test work? I mean, one can just try to use the ratio test here, but me looking at this, I can just see that this is just going to be 1, that limits. So if it's 1, then it means that we cannot conclude. So what next then do we say? Then we need to decide on this. Can we integrate this? Well, we can't integrate this.
Hello?
Yes, please.
Can we skip this question and do a different section?
Okay, that's fine. That's okay. You can always do that. Yeah, I was just carried by the sort of excitement we have on this. You can do a different section. A different section was there are lots of things looked at, but yeah, they're not like this one is the nth root. One question of its kind. It's so. What does the nth root say? Nth root means that you take the limit as n approaches infinity, and then you take the nth root, as this one says, nth root test, nth root of the modulus of an. Right. So this limit is either it's L. So L has 3 conditions. Either it is 1, less than 1, or bigger than 1. If it is 1, it's like the ratio test, so inconclusive. If it is less than 1, convergent, like the ratio test. If it happens that this limit is going to be bigger than 1, then it is divergent. So that kind of thing. We have this. This one, because if you differentiate the ln, the derivative of the ln, f of x. Okay, normally we use f of x for the integration part. Change everything to x. Okay, that's not what I'm saying. Effectively saying that if you integrate this one, you can just say let u be this. So let f of x be the ln of x. Let f of x be the ln of x. Let f of x be the ln of x. And therefore the derivative is 1 over, the derivative is 1 over x. Because it's 1 over x, then this x is going to cancel this. So this one is going to just be the integral test. Like, or it's going to work. If the integral test, okay, the integral test might be applicable, but it doesn't mean that we're going to have convergence, because we might have divergence like we had. If we have divergence because it's alternating, we must continue to use the alternating series test. Okay, this hinges on the first question that comes in this exam paper on the vanishing condition, which is an alternating series type always, but it becomes divergent and we do not proceed to check the alternating series test in the first question of the exam. Yet, in some instances, like in this case, we saw divergence there. Okay, so obviously that is brought by the fact that the question itself will potentially yield divergence under any extra examinations. And hence, the vanishing condition declaring divergence is a conclusive statement for us to close that question. Okay, this one, yeah. Okay, I'm speaking a lot about series. We have, see, I've gathered some questions. I think that I decided to gather some questions like this one. Okay. This question is about the Taylor series. Okay, I decided to speak about the Taylor a little bit. I think that it's an easy concept, but you need to understand it. But in this exam, it was said by one professor, and it is having all information, 100%. It has the remainder formula. So this one, you need to write it down because you need to memorize it. This one. Because sometimes it's not given. What is the formula for the Rn, 0? What is the formula? It is this. Always it is this. But now, in the question like this one, they said, remember to show that this limit is 0. But what is the Rn comma 0? What is it? It's this one. That's why I brought this question from a past paper. So it's there in the textbook, yes, this formula, but obviously we need to use it here. But it'll be very interesting to just look at the Taylor series question. Right, so let's look at the Taylor a little bit. Right, look at the Taylor. Let me just create a bit of space. I can either do this question or that. So find myself a bit undivided, a bit divided. All right. In a nutshell, what I'm saying is here you need to remember that the Rn0 is actually this, and the Ta, this one gives the Taylor polynomial formula. This is formula for Taylor series at the origin. Taylor series at the origin. So, okay, so we'll just look at remove this. Okay, let me just take note of this. So then we have this. What is Rn0? So Rn0, we know therefore that you just need to learn this formula. Is actually the nth plus first derivative evaluated at C is okay. So yeah, this is the formula for the Rn. So let's just practice the Taylor a little bit, but also we need to remember that obviously this is just Maclaurin. It's called Taylor here. In this module, 99% of the time they bring Maclaurin. What is the difference between Maclaurin and Taylor? The Taylor series is centered at the Maclaurin means that it is centered at somewhere we say A equals 0. Okay, it's n comma 0. Where am I now? Okay, right. So this one here, what is the formula for the Maclaurin series? Is this one. This question was set during when one professor was visiting professor at UNISA. He had taught at Wits University in Johannesburg for all his life, and he had retired at Wits University. When he had retired at Wits University, he was provided to, he visited UNISA to just participate and contribute and make a contribution. So he set some of the exams during his visit there at UNISA. Okay, so he sometimes applied he supplied much information in the exams, obviously because we are looking at the curriculum and he could give support in different modules in view of his experience in offering tuition at Wits University for almost his entire life. By the time he was setting this, he was possibly 70 or like 80 or something. He was extremely old. Okay, right. He might now have maybe playing with his grandkids at home. Okay, obviously not at all an issue there. But I want us to just to practice with this question a little bit. Okay, so I'm gonna keep this. I want to increase the slides. I want to add 2 more slides for us to just solve that problem. Um, right. Let's see what you get. So let me get to another slide. So right, we have another slide. Um, Right, one more slide. What am I doing now? I'm doing some autos. It's not what I want. Okay, just a minute. So have this. Right, so let's get started with solving this question. Just practicing. Right, so we're gonna consider here the f of x. So let me pick my writing pen. The f of x is e to the minus 3x. So what is this? So what is f of 0? Okay, okay, let me write this thing properly. Okay, because you're gonna have lots of derivatives here. And then now if we have lots of derivatives, there can be some problem. So now we have f prime, which is minus 3e to the minus 3x. Okay, if you find derivative of this, okay, you multiply this, the exponential function by the derivative of the top. That is how we differentiate the e function, right? Which is a special type of the exponential function. All right. Now, if you multiply the derivative of this one is minus 3, you multiply, it becomes 9. 3. So you have 3 by 27, it's 81. Okay, sometimes it helps to, okay, it's 3, 3 the whole time, so it's okay, never mind. It could be factorial, etc., but yeah, it works well. So the fifth derivative, okay, what is the answer? 3 by that is, 3 by 81 is 243, negative 243, e to the minus 3x. So you have this. We have this. You have this. Okay, we have this. You have this. Okay, so we want first the Taylor series. So the formula, we know therefore that t and 0 f of x is f of 0, f prime of 0, x1, f double primed, x squared 2, triple primed, quadruple primed. So you have this. What is f of 0? Is 1. F of 1 is minus 3. Um, which is x to the fifth power. Okay, so you're gonna have this, but as said indicated that this thing here, this one must stop at n because it's n here. It must stop at n. It must stop at the nth derivative. What is the nth derivative at 0? If we continue this, what would be the nth derivative? Can we find the pattern here? If we continue, okay, because it is positive, negative, positive, negative. At the first derivative is 0th derivative, 1, 2, 3. So it's just n, 3 to the power 5. No? 3 to the power n. Okay. Because now we are just observing the pattern here. So it's 3 to the power n, like this. It means that if we go here up to n, the nth derivative is we're gonna put it there. Okay. This one. Then you have fn 0x to the n over n factorial. Okay, you'll forgive me, it's a bit congested, but right, I'm trying to just demonstrate the idea here. So we come here now. In this nth one, okay, we have this. Okay. This is the nth derivative, but it must be multiplied by x to the power n. X to the power n. So we have this. Okay. All right. This is the thing that we got. Okay, we can even come here and generalize the nth derivative of this. Normally it helps. We need to generalize always. What is the nth derivative? So you can just take this one is minus 1 to the power n, 3 to the power n. Then it is e to the minus 3x. So this is what we get. So what do we achieve now? Okay. Now we need the r and 0, right? Of f of x, which is the remainder. Okay, we found the Taylor series, which is called the Maclaurin because it's at 0, centered at 0. We're substituting everything by 0 here. The x by 0 is called, it becomes called the Maclaurin series. Okay, now let's just do this one. All right, so this one, so we have this. And then you have n plus 1, like this. Okay, this is the formula. In this question, we have this one. We have Fn. Okay, the nth derivative of written at the bottom of the screen is this one here. The bottom of the screen, at the bottom of the screen, it's the nth derivative. So we carry it forward to the next slide. And then we have this. Right, when you get here, this one we know it's this. Okay. Um, let me remove this. Which is minus 1 to the power n, 3 to the power n. E to the minus 3x. Okay. Now when we get to this point, it is the nth derivative, but we need the nth plus first. So now you have nth plus first. So well, this one to the minus 3c. Okay, wherever there is a x, we put c. So we come to this one. We find now the remainder. Okay, so x. Okay, which is minus 1 to the power this. So we have this. Remove this pop-up. Okay, get this. Now in the place of the FC, we put this. F of C. Okay, I have this. So now you have this, then this one is minus 3c. Then it is x to the n plus 1 divided by n plus 1 factorial. Like this. From which we get the modulus of this. The modulus, then this becomes positive, this. You get this, n plus 1, 3n plus 1. You have this one divided by this. So now the modulus is going to remove the minus. Giving 3 to the n plus 1. And then this is that to the n plus 1 divided by n plus 1. Right, from which no, there's an error. This is E. Must be E here. I put a 3 there. Right, by error, so this one must be E. Because it is E in the original function and the derivative. Okay, so we have this one. So this one must just be E, this one must be E, and this one must be E. When R when okay, as n approaches infinity, so we come and we take the limit of this. Like you must just show that this limit is equal to 0. So we take the limit. Hence, f of x which is 3 to the n plus 1, 3 to the that. Okay, this x itself lies between 0 and 1. So this is a fraction, this. And the c itself lies between 0 and 1. So if this one is a fraction, then this whole thing is going to approach 0. That's because this limit of the absolute value is 0, it means the limit without the absolute value is 0. Okay. So this is like saying if they okay. How did yeah, there's an absolute notion here, because absolute convergence notion is just the modulus implication. Okay, anyhow, we're not really much into the absolute things of convergence, but we are effectively then saying here, because of this, then this limit here is what? Is 0. And therefore, we have shown this part, but also we have found the Maclaurin series. Where is the Maclaurin series? The Maclaurin series is this one here. Then, but we don't only show the Maclaurin series, we show that the remainder term approaches what? 0. As n approaches infinity. And what is the formula for the remainder term? It's this one. Please note it and memorize it, because tomorrow they might not even give it to you. Okay, so you have that. And then now you have this here, the limit is 0. And you got that this one is 0, and we are done there with this question. Okay, so we check something else. Right, I think that we'll need to take a short break. And now we can think about, I can try to gather some questions on the thing if need be, because the exam is going to be early tomorrow, 8 a.m. So can try to gather some questions on absolute and conditional convergence questions and series like that after some break. But I know that you might be tired as well mentally. So let me see. It's 6. Think about whether we can't meet again at 8:30. It's 6:30 now. It's just 6:37. Think about it and let me know. If I'm proposing that maybe I gather some questions, I'll need some time to find them in the book, prescribed book on the series and other things. But also I might.
Hello?
Yes, please. What do you think? Okay.
Can we end the recording?
Okay, that's fine. Let me just end the recording.